you appreciate what the accomplishment of human deduction. This is actually prove, not just have an opinion or just have empirical evidence, but actually have a mathematical proof that there are certain things that are doable by, in this case, by an algorithm or by a computer. There's often an expression that people say, you can't prove a negative. That's just not true. You can often prove a negative, and we do frequently, and here's an example of proving a negative. Okay? It's really good, that expression, you can't prove a negative, and if you want to show something exists, you can show it. I mean, there's a way of establishing it by just exhibiting it, if you happen to have it. But to prove that something doesn't exist, well, a lot of people say that can't be done. That's something that can't be done. But here's an example of proving a negative, which is kind of ironic because they're saying they have a proof that, anyway, for a moment, my brain went into a little spin there where it seemed like something ironic to point out, but now I've lost a moment. Anyway, I just want to emphasize that in the 20th century, that was the previous century, there were four big ideas that came from deduction. Lots of other scientific accomplishments, but there are four that are sort of considered as jewels of deduction. And one of them is relativity theory. How many people study special general relativity? Nobody? A few of you. You should. It's special relativity. It's really simple. If you know just basic Newtonian physics and the Pythagorean theorem from high school, you yourself can derive E equals MC squared by just simple considerations. So that's pointed to as one of the great jewels of deduction in the 20th century. The second one, and I'm looking together special and general relativity. And the second one is the idea of quantum theory, which also was basically a deduction, both tempered by experimental evidence, but sometimes after. And then the third one that people point to as being one of the great deductions of the 20th century and one of the mystical things that only a few people can understand, which is not true at all, is what I mentioned last time, Gödel's theorem. And Gödel's theorem proves that there are, one of the things, it proves that there are true statements about arithmetic, true statements concerning plus and multiply over the natural numbers that are not, they're true, but not provable. So, there are things that you can state about arithmetic that's true, but nobody can actually prove it. And then the fourth one is Turing's theory of undecidable languages, undecidable problems. And this is actually quite related to Gödel's theorem. And in the book, there's a brief introduction to Gödel's theorem and even a little bit of a sketch of Gödel's proof. But if you understand how this proof goes, and then you can understand, if you then understand the context of Gödel's theorem, the actual proof of Gödel's theorem follows a similar lines to what we did here last time. We did this in 15 minutes last time. When we finally got to the proof of this, it was just a simple little self-referential conundrum that, in the end, forms a contradiction and a proof. Okay, so I want everybody to appreciate that you've just been exposed to one of the great mysteries of the 20th century. There was a time when people said, there were 5 people in the world who understood relativity. Well, that was just silly. There was a time when there was only one person, but then once it was disseminated, and there were many. And similarly, it was said there's only 5 people in the world who understand Gödel's proof. That might have been true because the original paper, Gödel's paper, was very, very hard to read, but it was in German, so that made it harder. But now that the essence of that has been distilled and simplified, it's not that hard. And what we did last time with Turing's theorem on the halting problem is really not that hard. Okay, so today what I'm going to do is prove this again with a different approach. So last time we did it with something, a method that I call self-reference. And today I'm going to do it with a method called diagonalization. Diagonalization. Diagonally, you have to say that right, otherwise you go someplace weird. Okay, how many people got that reference? Thank you. At least a couple of people. All right. Anyway, there's diagonalization, and they're related in some ways. And the world seems to be divided into 2 types. There are people who think this is the simpler way of doing this, and there are people who think this is the simpler way. I find self-reference very confusing, and maybe some people did. And diagonalization is simpler, but other people have a different opinion. So I'll do both. Okay. But before I get to diagonalization, I want to go back a little bit and emphasize where we are in terms of the conceptual framework of where we are. This relates also to your homework 6, which I guess is the due date is today, but of course you have the extension time. And most of that homework, or many of the problems in the homework, ask you to prove, language, some language, just call it L at the moment, is decidable. I guess there's a D in there somewhere. Decidable. Okay. And you have to take the right conceptual level in order to tackle this. Okay. So this is asking for, let's actually take, what's it called? ADFA. Okay. So ADFA is a set of, we're given a DFA M, W, such that M show how the DFA-M can decide W, whether W is in the language or not. What you have to do is have a Turing machine that it has input M and W, a description of that DFA and the input W, and let's give a name to the Turing machine, M prime, and M prime has to decide if the DFA-M accepts W. Okay, so you have to focus on the Turing machine that takes in the description of the DFA. All right, so that's a different level of abstraction, a different level of attack. Now, in this particular problem, what does the Turing machine M prime do? I heard the word simulate. Yeah, it simulates M on W. Okay, so this one isn't so mysterious or difficult to think about. Okay, but now let's take a different one. Let's take all DFA, which I think is on your homework. What is the actual symbol that's used for a DFA in the homework? Do you know? Anybody remember or have it in front of you? I'll call it M. M accepts all strings. Okay? So now, simulation doesn't make sense anymore for this problem, because what would you simulate? This is a question about all possible strings. Okay? You can't simulate this DFA on all possible strings in order to make a decision about whether the DFA accepts all strings or not. Okay? You can't get your Turing machine that takes in that. The Turing machine cannot take in the description of this DFA and then start generating input and testing each input to see whether or not the DFA accepts that input or not. Okay, so that would be thinking too low level. Instead, this Turing machine M prime has to have within it some idea. You have to give it some idea and encode it in the Turing machine that allows it just to look at the description of this DFA and therefore decide yes or no, accept or reject if M accepts all strings. Okay, and so you have to think about how you, if you were given a DFA, would look at that DFA and decide whether or not that DFA accepts all strings or not. Yes. Once you see the idea of how you might do it, then you have to encode that idea into a Turing machine that can do that same thing. Okay? But the main point is that this is a more abstract question than whether or not a particular DFA, accepts a particular string or not. Okay? Or even whether a particular DFA accepts all strings. Okay? If I show, one problem would be I show you a DFA and I say, does this DFA accept all strings? Okay? You can look at that and you can figure out yes or no. Okay? That's a lower level question here than saying, build a Turing machine which can be given any arbitrary DFA, and that Turing machine has got to be able to decide whether that arbitrary DFA accepts all strings. Okay? So I just emphasize this because in office hours this week, I could see there were some people who were not getting the context of the problem, the context of what needs to be decidable. That it is a more high level and abstract question. Now I was trying to think of a good analogy to make this distinction clear, and I didn't succeed, but I'll give you a bad analogy. Maybe people will understand anyway. So let's say you have some candy machine, okay? And it has, various types of candies, Mars bars or whatever. And it's got a place where you put in the money. Okay. And you might ask, does this candy machine work correctly when I put in the money and I ask for a Mars bar? Okay. Well, that's, I'll simplify it. Does this candy machine work correctly the next time I put in the money for a Mars bar? Okay. Well, how would you answer that question? I mean, you put yourself in the position of you're the service person for this candy machine, and you want to know, does this candy machine work correctly, will it work correctly the next time somebody wants a Mars bar? What would you do? Somebody's got to know. Come on. 64 people are. What do you what? Yeah, you put in the money, try the thing, and see if it works. Okay, you get yes or no, the thing worked or it didn't work. All right. So that's a very specific low-level thing, and this is a specific, let's say this is a specific DFA, and you have a specific input or question. Will it work when you, W is sort of the question of will it work the next time somebody wants a Mars bar? Okay, so you have that question. But we got another question, which is, you're just given the machine, you're given the candy machine, or machine candy if you speak French. You're given the candy machine, and you're asked, will this machine always work? Okay. cancer.